Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on September 18, 2025, just yesterday. The standout result is a new optimizer that cuts memory use for matrix-shaped parameters while reaching an epsilon stationary point with sample complexity O of epsilon to the power of -3, improving on prior Muon analyses. The paper is titled LiMuon, Light and Fast Muon Optimizer for Large Models, and the implications for model training are quite significant. In short, it pairs momentum-based variance reduction with randomized singular value decomposition to keep states small and still converge on both standard and generalized smoothness, with language and vision experiments backing it up. On X, a post highlights LiMuon using low-rank momentum compression and variance reduction for faster, lighter training with shared figures and code blocks, drawing about 160 likes and moderate engagement. Alright, the previous figures set the stage with method intuition, and Table 1 now contrasts optimizers head-to-head. The table reports sample complexity, state memory, and whether guarantees hold under generalized smoothness, which means the loss can be less tightly curved than standard smoothness. LiMuon matches the best O of epsilon to the -3 sample complexity, while reducing state memory to about m plus n times r hat. Crucially, it does so without large batches, so every step can use a batch of one. Okay, the previous table contrasted guarantees and memory. Figure 1 shows how the method stores a compact momentum, replacing the full m by n matrix with 3 skinny pieces from randomized singular value decomposition. The left block represents the large momentum mt, which would cost m times n memory. The 3 right bars represent u hat, s hat, and v hat transpose, so storage drops to about m plus n times r hat, since r hat is much smaller than both m and n. Alright, the previous table compared guarantees and memory. Figure 2 shows training and test loss over iterations for DistilGPT2 on Wikitext 103 across 7 optimizers. The dashed pink LiMuon option 1 curve drops fastest and ends lowest, which indicates stronger optimization. The solid yellow LiMuon option 2 tracks closely behind, so compression barely hurts loss while saving memory. Atom and Atom W decline more slowly, and Muon Plus sits between Lion and LiMuon. So the previous figure highlighted loss curves for DistilGPT2. Table 2 presents a head-to-head comparison under identical training, reporting memory in gigabytes, plus training and validation perplexity. LiMuon option 1 achieves the best perplexity, with 142.85 in training and 170.34 in validation, while using 6.30 gigabytes. LiMuon option 2 trades a bit of perplexity for lower memory at 6.05 gigabytes, which underscores the benefit of momentum compression. So the previous table covered language model perplexity and memory. Table 3 summarizes tiny ImageNet results for the ViT model, listing memory in gigabytes and both training and testing accuracy. LiMuon option 1 delivers the top testing accuracy at 26.59 with 4.09 gigabytes. LiMuon option 2 trims memory further to 3.85 gigabytes while holding a solid 23.61 testing accuracy, which shows the compression traded a little accuracy for clear savings. Wrapping up, 2 takeaways stand out. LiMuon reaches epsilon to the -3 sample complexity while cutting state memory through low-rank randomized singular value decomposition, and it keeps those gains under generalized smoothness, which better matches real training. The broader implication is leaner, scalable optimization for language and vision models. Thanks for listening. I am Alex, signing off.